Hey guys, Wilkes here. So let's actually talk a little bit more about nuclear chemistry. And in particular, we're going to talk about half-life and what half-life is and how does it work. So let's just jump straight in and start doing the define it. So half-life. And half-life is simply the amount of time for 1/2 of a radioactive isotope to transform. Okay, it's simply the amount of time for 1/2 of a radioisotope to transform. So, example here. My radioisotope right here, it is 6, 7, 8, 9, 10. Radioisotope green balls. Okay. It will transform into 1, 2, 3, 4, 5. Into blue balls and green balls, because these aren't transformed yet. With the time it takes for it to go from 1/2 down to this is its half-life. So that time, this T, the time it took there, is the half-life. Okay? Let me show you a quick video so you can see how it looks on a graph, and then we'll come back and talk about some common isotopes.
Radioactive iodine-131 decays by first-order kinetics. After 1/2 of the isotope has decomposed, the time that has elapsed is termed the half-life. The isotope amount drops again by half in the time period equal to the half-life. After the third half-life, the amount of radioactive isotope has dropped to 1/8 of the initial amount. After 7 half-lives have elapsed, less than 1% of the original amount of isotope remains.
So after watching that short video, we can see how radioisotopes actually change and the time it takes and see that when it transforms at. So let's take a quick look at what are some common half-lives for some elements and what does that look like? And so let's just click on over. I'm going to go to my desktop here. And we can see this is a chart I just pulled offline. And we can see there's a whole bunch of elements here with a varying amount of half-life. So we can see all these different half-lives they have and what type of decay or what type of emission takes place. For example, here we can look at polonium-218. It decays by alpha emission. And it has a half-life of 3.5 minutes. Okay, or 3.05 minutes. Look, acetane here has one of 1.6 seconds. Fluorine 15, look at that. That is 10 to the minus 22 seconds. I believe that's 4.1 like femtoseconds. So really, really short times. But if we scroll down here, we can see, we can look at like indium 115. We can see it has 10 to the 15 years. So that's like, so 10 to the 9 is billion, quadrillion, quintillion years before due. The Earth has only been around for 6 billion. So it's going to take a really long time for indium to decay, but it does still decay. Okay? So let's actually go back to a table and actually figure out ways that we can solve this problem. Okay? So, if a scientist has 40 grams of radon-222, how much radon-222 is left after 15.2 days. The half-life of radon 222 is 3.8 days. Okay, so the easiest ways for us to solve this problem is by using a table to help us figure this out. And it's actually going to be a 3-column table. Okay, so first column here is going to be number of half-lives. Okay. Time, and I'm going to put in parentheses days because that's what the unit we're using in, and then amount, and that's going to be in grams, so I don't have to use these different units, I just type them off. So starting off at the very beginning, I can see that I start with 40 grams, so I can fill this out by putting 40 there. Okay, the time is, since it's the beginning, it's going to start off at 0 time. And number of half-lives, since I'm at the very beginning, is also 0, because no time has passed, so both the number of half-lives and time have to be equal to 0. This is the biggest mistake students make. Listen up. It always starts off with 0, 0, and the amount. Okay? Now, after 1 half-life has passed, 3.8 days have passed, okay? That's how much time has passed after 1 half-life. The amount of material that has actually been lost or converted over has now become 20. So I'm at a half of what it was, okay? Now, at 2 half-lives, which comes out to 7.6 days, I've only got 10 grams of material left because another half-life, so half of this has gone down from this point. Again, third day, oh gosh, now I'm gonna have to think, so that's gonna be 11.4 days have passed. I'm gonna end up with 5 grams. Finally now, I'm gonna see after the 4th half-life, which is now 15.2, I end up with 2.5 grams. Okay? So the correct answer in this case would be 2.5 grams is left over. Okay? So the big thing we need to do is that we need to make a table with our times and with our amounts. I might give you like maybe the ending amount and you have to work your way backwards, and I might say something like you have 3 half-lives have occurred, how much have you started with? But the same idea holds true. You create this table and you go from there. So let's do one more example together. Okay? So another way of looking at it is this question here. Thorium-233 has a half-life of 22 minutes. Okay? And the scientist has 4 grams of thorium-233 after 44 minutes. How much should they start with? So again, I'm going to start the table by building it out. So half-lives, okay, time, and amount. So I'm going to start off with my time, which is going to start off with here with 44 minutes. Okay, I know the half-life is 22, so I've got to divide 44 by 22 to get that. I can do it 2 times, so I know there's going to be 2 half-lives. So I'm going to go backwards, and it's going to be 22 minutes, and then I know it's going to be 0 minutes. Okay, I also know that time is going to be at 0 here. 1 half-life, 2 half-lives. Okay, now it said here at the beginning, I started with 4 grams. Since I'm going backwards, I need to double it every time. So I'm going to start off with 4. It was 8 at that time, and now it's 16 grams. So my final answer to this problem would be 16 grams of thorium-233 is what they started with. Okay? Simple as that. Thanks again. I hope to talk to you tomorrow.